Delaware Tech, Chemistry 100, Chemistry 110, Unit 5 continued, molar mass. The molar mass is the mass of 1 mole of any substance, and it is useful whenever you need to convert mass units like grams to moles or moles to grams. Before we talk about molar mass, let's just remind ourselves of what atomic mass is. Remember, the atomic mass is the mass of one atom, and more accurately, it's the average mass of one atom, because remember, each type of atom from each element can have multiple isotopes, so it's the average of all the isotopes for that one atom. And we measure that mass in Daltons or atomic mass units. If we were to add those up for a single molecule, we would get the mass of one molecule. So if we added all the atomic masses of all the atoms in that molecule, we would get its molecular mass, also in Daltons. And if we did that for a formula unit from an ionic compound, we would also get the mass of a single formula unit in Daltons. And these values are very, very tiny because the unit Dalton is an incredibly tiny unit. Now, so if you were to look at the atomic mass of hydrogen, for instance, you know right off the periodic table, it's 1.00794 Daltons, or atomic mass units. And if you wanted the molecular mass of water, well, you would just add up the mass of 2 hydrogens plus the mass of 1 oxygen to get 18.0153 Daltons. And likewise, we can do this with formula units such as sodium chloride. We add up the mass of a sodium atom and the mass of a chlorine atom, and we get 58.443 Daltons. And you can even do this for very large molecules like proteins. And this is the molecular mass of albumin. It's a little over 64,000. So that's a bit bigger in terms of the size of molecules. Now, molar mass is the mass of 1 mole of a substance. So if we did that, we would have very, very large numbers of Daltons, but we don't use the unit Dalton. We use the unit grams per mole. In other words, we're asking the question, how much does 1 mole of a substance mass out to, or how much does it weigh in grams, if you were. So this unit will actually, it'll be a different unit for molar mass, but the value, the number, will be identical. So if you look at all these molecular masses and formula unit masses, etc., you will get the exact same value in terms of the number, but the unit will be different. So the molar mass of hydrogen atoms is 1.00794 grams per mole. The molar mass of hydrogen gas would be twice that because there are 2 hydrogen atoms, and the molar mass of water would be the mass if you added up 1 oxygen and 2 hydrogens, just like we did before. But you'll notice that the unit has changed. And the same goes when you're even dealing with larger molecules like albumin. We still get the exact same number, a little over 66,000. What is different here is the unit, and this is very important, because this is the mass per mole. In other words, if I had a mole of albumin, if I had 6.022 times 10 to the 23 molecules of albumin, they would weigh over 66,000 grams per that 1 mole. Now, you might look at this and say, well, that's a big coincidence that these numbers are identical when we're talking about many, many atoms or many, many molecules or formula units than when we're just talking about 1. And that's right, it is a coincidence in one way, but it is not in another way. The reason why these two sets of numbers are identical is because Avogadro's number was picked purposely to make sure that these two numbers were identical. So the mass of 1 atom in Daltons is the same mass in grams per mole of a mole of that material. And that is because the Avogadro's number, or what we call the mole, was picked to be very specific to make sure these two pairs of numbers match identically. So, the atomic mass, remember this is the mass of 1 atom. We have a molecular mass, that's the mass of 1 molecule. And the formula mass, this is the mass of one formula unit. So these are certain numbers of Daltons or atomic mass units. Now the gram atomic mass, the gram molecular mass, and the gram formula mass are the mass of 1 mole. So it's just like the molar mass, except we're only asking the question, how many grams in a mole? And you just give the gram unit. So the difference between gram atomic mass, gram molecular mass, and gram formula mass versus molar mass is the fact that instead of saying it's this many grams in a mole, we say it's this many grams per mole, and we just say it together. And while you will find in textbooks gram atomic mass, gram molecular mass, gram formula mass occasionally, I am going to be really limiting my use of these terms for most of our problems, and we're going to be strictly using molar mass. And the reason why we use molar mass is the unit has grams per mole. And this allows this unit, this value, unlike the other sets of values above, to be conversion factors. Anytime you have a unit that is composed of one unit divided by another unit, it allows you to convert other values of, in this case, grams to moles or moles to grams, because both units are in the whole unit of the molar mass. And we would do that by just slightly modifying our molar mass to look like the ones in red. So what was, let's look at the molar mass of sodium chloride. It was 58.443 grams per 1 mole. Well, that means it's 58.443 grams of sodium chloride per 1 mole of sodium chloride. In other words, 58.443 grams of sodium chloride is the same thing as 1 mole of sodium chloride, and therefore putting them together as a fraction like this are conversion factors because they're really disguised versions of 1. The top, the numerator, matches the bottom, the denominator. They're the same value in each case. So let's look at how to calculate this. So you need to add up all the values of the individual elements in each compound, keeping track of how many of each atom there are. And if we look at calcium phosphate, for instance, Ca3, parentheses PO4, close parentheses 2, this tells you there are 3 atoms of calcium, there are 2 atoms of phosphorus, and for the oxygen, remember, everything in the parentheses is multiplied, so we have 8 atoms of oxygen. We know the atomic masses of each of these, they're right on the periodic table, and the atomic masses are the same values, the same numbers as the molar masses for each of these atoms, just in grams per mole. So we would look up those molar masses or atomic masses of each atom, and then we would multiply how many atoms times the respective molar mass of the atoms to get the total contribution of each type of atom. And none of these numbers on the right, the 120.234, the 61.9475, etc., they don't mean a lot by themselves because they contribute to the total mass of the calcium phosphate. So you need to add them up, and then you get this value of 310.177 grams per mole. And what this tells you is if you had a mole of calcium phosphate, in other words, you had 6.022 times 10 to the 23 particles of calcium phosphate, then you would have 310.17 grams. 1 mole of this equals this many grams of this. And therefore, this is a conversion factor, and you can write it with the 310 on the top or the 310 grams on the bottom, because it doesn't matter. The two are equivalent to one another. 1 mole of calcium phosphate is 310.177 grams of calcium phosphate. And therefore, you can use a molar mass to create one of 2 different conversion factors for calculating conversions of grams to moles or moles to grams. So let's practice looking up or calculating the molar mass of each of the following. Well, with atoms, you just look them up. Argon, iron, uranium, those are just the atomic masses with a new unit, grams per mole. That's simple enough. Oxygen gas, which is O2, well, it's 2 times the oxygen. Oxygen is about 16. It's 15.9994 grams per mole. You just multiply that by 2. And you go through these, and I'm not going to go through all of these. Just make sure that when you go through them, you count up all the atoms. For instance, with ethanol here, you see there are 2 carbons. There are a total of 6 hydrogens. You have 5 in the formula in one part and 1 by itself at the end. So make sure you have 6 hydrogens and 1 oxygen. If you don't see a number, remember that means there's only 1 of that atom. If you look down here, magnesium nitrate, remember the 2 is multiplied by everything in the parentheses. If you look at magnesium sulfate heptahydrate, that means for every MgSO4, there are 7 whole water molecules. So you have to include 7 times 2 hydrogens, 7 times 2 oxygen, 7 times 1 oxygen plus the 4 from the magnesium sulfate in your totals. And you're going to go through and do that in each case. And this last one is a little tricky. You have to be careful because there are a total of 28 oxygens there. So why do we need this? Well, when we're in the lab, we can't measure moles directly. We can measure grams of mass directly. That's especially useful for looking at solids or liquids. We can measure the volume of substances directly. This is especially useful for gases, but it's also useful for liquids and occasionally for solids. But we really need to know the moles. Chemistry is done in moles. Chemistry reactions don't care how heavy they are or how much volume they take up in general. There are exceptions, of course. But the most important part is how many of each atom or each molecule are reacting. And the way we count them is in moles. So while we can measure grams of mass or liters or milliliters of volume, we really need to know how many moles there are. And that's why we use the molar mass value to convert it. And every single substance will have its own molar mass. So unlike before when we were using Avogadro's number to convert number of molecules or formula units or atoms to moles, there you can use one conversion factor for everything. Avogadro's number works for everything. But when you're going from grams to moles or moles to grams, you need a unit that has grams and moles in the unit. In molar mass, it's grams per mole, so both units are there. And that means you have to determine the molar mass of every single substance that you are calculating the grams or moles of. So each substance will have its own molar mass conversion factor. And this is the quick and dirty way of converting it. If you want to go from grams to moles, you take grams and you're essentially dividing by the molar mass. And that will give you the moles. And if you have moles, you're multiplying by the molar mass. And you'll notice that will give you grams. So if you look at each of these cases and you write down the molar mass on the bottom in this case, you'll notice the grams cancel the grams and you're left with moles. Whereas when you want to go from moles to grams, you put the molar mass the way it is and the moles will cancel the moles and you'll be left with grams, which is what you want. So be careful how you use it. And just as a reminder, we have this algorithm chart that you were all given among your handouts in the beginning of the semester, and I'm going to cover the 2 side ones because we don't need them for this unit. We're really only going from particles to moles or moles to mass or backwards from mass to moles and moles to particles. And remember, particles can be atoms, molecules, or formula units, or even ions. It doesn't really matter as long as it's a particle. If you're going between particles and moles and you want to convert one to the other, or vice versa, you need Avogadro's number. It's the same conversion factor every time. But if you want to go from moles to mass or mass to moles, those are the 2 bottom ones, you need the molar mass of that particular substance, and that is different for every single substance. So you need to get, as soon as you see a problem where you need to go from grams to moles or moles to grams, you need to find the molar mass first. So here are some problems. These are problems that all involve conversion to grams to moles or moles to grams in one way or another. How many moles of magnesium are in 24.305 grams of magnesium? Well, you're asked for moles, you're given grams, so you need the molar mass of magnesium. Well, you just go to the periodic table. It's a single atom. That's easy enough. And it turns out the molar mass of magnesium is exactly the same number. It's 34.3050 grams per 1 mole. And if you write any conversion factor, remember, when we write conversion factors, there is a process here. You start with the thing you have. Actually, the thing you have is this amount of magnesium. So you write that first. Then you create a conversion factor by making your parentheses and a dividing line. Then notice that you're destroying the unit grams of magnesium and you're creating the unit moles of magnesium. So to destroy this unit, you need grams of magnesium on the bottom, and to create moles, you need the moles of magnesium on the top. Pardon my horrifying penmanship here. And if you have moles on the top and grams on the bottom, that will allow you to then put in the appropriate numbers. And I'm gonna erase my mess here, and you can see that I have put the gram part of this unit on the bottom in the denominator, and I put the mole part in the top. And it's always 1 mole is equivalent to a certain number of grams of a substance. That is what molar mass is derived from. So the other problems are essentially the same format, except you might reverse the conversion factor. So here, the second problem, we have 2.34 moles of carbon dioxide, CO2, and you're asked for the mass. So you always start with the thing you have, 2.34 moles of carbon dioxide. You build your conversion factor, 2.34 moles. And if you're doing harder problems with multiple substances, you really want to write carbon dioxide in there. You want to say moles of carbon dioxide. But for single substances, we're only dealing with carbon dioxide in this problem. You don't really need to write the carbon dioxide. But keep in mind, if you're doing more complex problems, which you'd see in Chem 110, you do need to write it down. So now we know moles will be on the bottom because that's the unit we're destroying, and we're putting grams on the top. Well, we need to know the relationship. How many grams are in 1 mole of carbon dioxide? Well, that is the molar mass. And if we add up 2 oxygens and 1 carbon, we will find that we get a molar mass of 44.0095 grams per 1 mole. And I'm writing the molar mass as a conversion factor. And in this particular problem, you want the number of grams on the top, and you want the number of moles, which is going to be 1, on the bottom. And you will calculate your answer. And I'm going to delete this mess here because we have it nicely printed out here. And you can see. And you can do the same thing with the next problem. You're asked for the moles of sodium chloride, and you're given the number of grams. So you need a molar mass. And I'll pause here. You can stop for a second. Now I'll show you the answer. You calculate the molar mass of 58.443 grams per 1 mole, and you place them in the right position of your conversion factor. And the last problem involves glucose, so you have to do a little work to figure out the molar mass. You're given the number of moles, 4.07 times 10 to the minus 4 moles, and you need to convert it to mass units, so you have to calculate your molar mass, which is about 180 grams per 1 mole of glucose. And when you plug this in, you can get your value. And you will notice that when you do this, your values should make sense to you. Look at this last problem. We have a very small number of moles, so we should expect a very small number of grams. If you go back to the, say, the second problem, we have a little more than 2 moles of carbon dioxide, and we know that each mole of carbon dioxide has a mass of about 44 grams. So our answer should be a little more than double 44 grams, and 103 grams is about right. So always make sure your answers make sense. And we have one more set of problems, and this takes advantage of both of the conversions you've learned. The moles to grams, grams to moles that we just did, as well as the previous conversion of particles, meaning atoms, ions, molecules, or formula units, to moles, or moles back to particles using Avogadro's number. So in these problems, you will need to use both, and you can do them separately or you can do them together, stringing together your conversion factors. So the first question says how many formula units are in 17.98 grams of magnesium nitrate? Well, we always start with the thing we have, and we have this many grams of magnesium nitrate. And we convert that into moles using its molar mass. So you first have to determine the molar mass of magnesium nitrate, and this is your value, 148.3148 grams of magnesium nitrate per 1 mole of magnesium nitrate. But remember, we want the grams on the bottom and we want the moles on the top. And that will give us our answer in moles, but we're not done. We're asked for formula units, and you already know how to convert moles to formula units. You just multiply by Avogadro's number. And while it says formula units of magnesium nitrate, moles of magnesium nitrate, the fact is this conversion factor, Avogadro's number, or Avogadro's constant, is good for every single substance. So one of these conversion factors you have to calculate, and one of them you just remember is 6.022 times 10 to the 23. The next problem goes in the opposite direction, where we start with the number of molecules, which is a type of particle of glucose, and we're asked for grams. So now we can do this together in one shot. We can put both our conversion factors. We always start with the thing we have, 3.50 times 10 to the 9 molecules of glucose. We build our conversion factor based on Avogadro's number to convert molecules to moles of glucose. So if you stopped right here, you would end up with the molecules of glucose. And then you convert molecules of glucose to grams of glucose by using the molar mass, and that you have to calculate. So you have to add up all of the atoms' molar masses, the 6 carbons, the 12 hydrogens, the 6 oxygens, to get this number of 180.1559. And you see you're just really multiplying that through. I've broken this up, so if you had done it in 2 steps, this would be your answer in moles for the first part of the calculation, and then this would be your answer in grams for the second part of the calculation. And you can see that starting with 3.50 times 10 to the 9 molecules of glucose, this looks like a lot of molecules of glucose, 3.5 billion molecules of glucose. But the fact is that's not many in terms of molecules, and we end up with this incredibly tiny mass, just above 1 times 10 to the minus 12 grams, or about 1 picogram. And I'll delete that, and then I'll let you go through the rest of these. You have how many atoms of iron, and this is easy because you just look up the molar mass for iron and you know Avogadro's number, so you can convert that. And I'll pause here for a second. You can stop and try it on your own. And here's the answer. And the last one is taking 1 formula unit of sodium chloride, and you're asked for the mass. So 1 formula unit of sodium chloride, you know that it weighs 58.443 daltons, because that's the molar mass in daltons. That's the molecular mass, that's the formula unit mass of sodium chloride. But what you're asked for is the mass in grams. So you have to do the same thing as you did in the second problem. So instead of starting with 3.5 billion molecules of glucose, you're only starting with 1 single formula unit of sodium chloride, and you're going to end up with an incredibly tiny mass of your sodium chloride. So in fact, this answer here is in grams. This is the mass of 1 NaCl. But it's also, but you'll remember 58.443, that number you calculated as the molar mass, is also the mass of 1 formula unit in Daltons. So these two are actually the same value in 2 different units, because what you've done here is Avogadro's number is your conversion factor. And remember, I told you that Avogadro's number was picked purposely so that these two match, and that this mass here, I'm saying that this molar mass in grams per mole is the same as the mass of a single formula unit in Daltons. And with that, we'll stop here.